Hello everybody, I would like to welcome you to my lecture entitled Possibilities and Limitations of 4D Biofabrication. In this lecture I will try to highlight our recent development in this field, and at the end I will share with you my ideas what could be improved in this field. Before I start, I would like to first thank my group, the members of my group, for their hard work and for their contribution to this research. Why research which we do is very important? Everybody knows that the number of people living on the earth is increasing, and people get older, average life expectancy increases. There is constantly growing need of organ replacement. We need donor organs. And the number of donor organs is insufficient to cover our needs. So practically, we would like to have a possibility to replace natural organs with engineered ones, what will basically allow us to solve the problem of the lack or insufficient number of the donor organs. In order to do it, one needs to understand that our organs have complex three-dimensional structure, and practically we need the technology which allows us to reconstruct this three-dimensional structure. The best family of the technologies available on the market is 3D bioprint. We offer a number of advantages, such as possibility for deposition of materials locally. One can deposit different materials, this process automatized, and what is very important, it allows individual adjustment. On the other hand, most of the methods suffer either from insufficient resolution, difficulty with fabrication of the hollow structures, problem with the cell orientation, provided mechanical anisotropy, and also oxygen diffusion. As example, I'd like to show you what one can do in the field of the fabrication of vascular elements. If one uses 3D bioprinting, there are two options. Either one prints sacrificial material inside the matrix. So sacrificial material is a green one, matrix is a red one. One can make sacrificial material fluid and remove it by applying high pressure. This approach works nicely if the tube diameter is relatively large. Decrease of the tube diameter, so channel diameter, shall result in the increase of the pressure which applied to remove the sacrificial material. So practically, as a result, it can lead to a situation what the whole structure will burst upon the applying of a high pressure. Second possibility is a direct printing of the tube. This approach again works nicely for relatively large structures, but as soon as we try to fabricate small blood vessels with diameter less than 1 millimeter, one needs to apply very high, or one needs to have very high resolution, and high resolution is normally achieved by applying high shear force, which is often negatively affects cell viability. So both approaches are not perfect, and it's still difficult to make complex hollow three-dimensional objects by conventional fabrication approaches such as 3D printing and other technologies. Where to find a solution? One can have a look around and find inspiration in the origami. Most of you know what is origami. Origami is the traditional Japanese art of a paper folding. You take a piece of paper with ornament on it, you fold it and get some kind of an object with a complex surface part. Very interesting concept. So practically we can try to use this approach for fabrication of a complex three-dimensional objects used for tissue engineering. One needs to simply find a way how to achieve this shape transformation. One possibility is to again look around and to find inspiration in nature. Most of you have seen pine cones, and most of you paid attention that pine cones are closed in summer when humidity is high, and they open in fall when humidity falls down. The pine cone uses this mechanism of opening for dissemination of the seeds. The most important for us is to understand why it happens. Pine cones have bilayer structure with different orientation of cellulose fibers. The cellulose fibers do not extend upon the swelling, but only the distance between them can change. So practically what happens in summer humidity is high, and this blue layer swells and the pine cone is closed. The infall, the blue layer shrinks due to its drying, and the pine cone opens. So the main message here is what we need at least two kinds of materials with different volume expansion properties to get shape transformation. And this approach can easily transfer to the synthetic material. We just need to fabricate a bilayer which consists of two materials. One of them can be hydrophobic polymer, like for example polycaprolactone, and second polymer can be any kind of a swelling hydrogel. In this particular case, we have used thermoresponsive polymer, which is able to change its degree of swelling upon cyclical change of the temperature. As you apply the temperature at which the polymer swells, so basically it is low temperature, then the bilayer rolls and the tubes are formed. This approach works. And of course, one can transfer this approach for the biofabrication. One can simply put the cells on the surface of this bilayer, apply a different temperature, the bilayer rolls, makes the tubes, and the cells get encapsulated inside these tubes. Approach works. And if one properly plays with the shape of the bilayers, one can get different kind of complex three-dimensional structures. And this is what we try to do in our lab. So we try to explore approach which we name 4D biofabrication approach. Why 4D? Because we first fabricate some kind of three-dimensional object. In this particular case it is a layer, and then it undergoes shape transformation, so practically it changes shape in time, and time is a fourth dimension. We do not name it 4D bioprinting because in this case we use not only 3D bioprinting for fabrication of the initial object, but we are free to use any kind of additive, formative and subtractive manufacturing technologies. The advantage of this concept, if you for example think about the blood vessels, is what we don't need the very high resolution for fabrication. We don't need to remove the sacrificial material because we don't use any kind of sacrificial material, and we can precisely control the quality of the layers. How to transfer this shape transformation concept to 4D biofabrication approach? There are practically three options. First option is what we first fabricate a flat structure, then it undergoes shape transformation, and then we put cells inside. Practical advantage of this particular concept is not that high because we first fabricate complex three-dimensional structure and we need to put cells somehow inside it. It's very difficult. So which is why we do not use this approach. Another concept consists in the first fabrication of the object, then we deposit cells on it, and then already object with the deposited cells undergoes shape transformation and a complex three-dimensional shape is formed. The third option is when we put the cells inside the object, and then after shape transformation we get the cells inside the folds of a formed three-dimensional object. Practically for us are the most interesting approaches B and C, second and third approaches. And today I will show you examples of application of these approaches for biofabrication. We need to think about the materials which we use. Of course, the materials which we use must be stimuli responsive and shape changing. There are many kind of such kind of materials: hydrogels, shape memory polymers. Of course, materials must be biocompatible and biodegradable. So not every hydrogel, not every shape changing every shape memory polymer is biocompatible, biodegradable polymer. So our choice decreases. Next, stimuli which is applied for in order to cause a shape transformation must be biocompatible. One can, for example, use changes of the temperature within temperature range between 0 and 37 degrees Celsius, or, for example, apply calcium ions. And in the case if we would like to put the cells inside the material, also deposition of this material, the cells, must be biocompatible. so cells must withstand this deposition process. So it means out of a huge realm of shape-changing polymers, we have to choose only a small fraction, and practically at the end, we don't have anything. And what we try to do in our lab, we try to find out ways how to use standard biocompatible, biodegradable polymers and materials which are used in tissue engineering as materials for the 4D biofabrication. And we developed 4 approaches. I would like to today show illustration of this approach. First option consists in the switching of the swelling. So practically fabricate a bilayer. One of the layers changes swelling properties when temperature of calcium ions are applied. As a result, the shape transformation occurs. This approach was demonstrated on an example of a layers made of hyaluronic acid and metacrylated alginate. Both polymers were metacrylated to make them photocross-linkable. From chemical point of view, both these polymers are weak polyelectrolytes because they contain carboxylic acid, and their swelling properties, of course, depend on the presence of the bivalent ions. Without calcium ions, the polymers, if of course cross-linked, swell a lot. With calcium ions, the swelling is substantially reduced. So we practically can use addition or removal of the calcium ions as a stimuli to cause the shape transformation. So we make a solution of these polymers, either without cells or we add the cells, we print it, then we shine the light to cross-link the polymers, we expose it to the physiological buffer environment, like for example cell culture media, and the formed structure folds and makes the tubes. So this is how the tubes look like. The tubes are formed in the media without calcium ions, like it was shown here, and applying the calcium ions leads to the unfolding of the folded structure. The process is very reversible. As soon as you remove calcium ions by, for example, applying the DTA, the tubular structure is formed. As soon as we remove the calcium, add the calcium ions, the structure unfolds. Very interesting, in this case, we didn't fabricate a bilayer, but the structure was still able to form the tube. Why it happens? We believe it's due to the formation of vertical gradient of the cross-linking density. So practically top and the bottom layers of this printed structure have different cross-linking density. As a result, we have different swelling properties, and this difference of the swelling properties causes the shape transformation. The diameter of the formed tubes ranges between 10 micrometers and approximately 200 micrometers, depending on the dry thickness of the layer. So it is the diameter of the tubes of the blood vessels which are most difficult to fabricate. So in this particular approach, we are able to incorporate the cells inside the walls of the formed structure, like it was shown here. The second approach consists or based on the dissolution of sacrificial material. The idea is illustrated here. We fabricate a bilayer which consists of two biocompatible, biodegradable polymers, gelatin and polycaprolactone. Both of them were cross-linkable by the UV light. So practically we shine UV light through the mask, cross-linkable polymers in this area. In this area we remain uncross-linked. We apply the solvent to dissolve non-cross-linked polycaprolactone, so it is organic solvents like chloroform, and afterwards we get a kind of a complex structure. If you expose this complex structure to cold water, both gelatins cross-linked ones and non-cross-linked ones swell with the same degree of swelling, so practically it simply leads to the lifting of the polycaprolactone. The bilayer is not able to fold because it is basically held by the non-cross-linked swollen gelatin. And only if the temperature increases to 37 degrees Celsius, this non-cross-linked gelatin is dissolved and the bilayer can roll and make the tube. So practically we are able to manipulate this structure at 20 degrees Celsius. We can deposit cells on it, and the three-dimensional object is formed only if the temperature increases to 37 degrees Celsius. So it allows us to precise selection of a time when we would like to have shape transformation. So approach works very nicely. So the bilayer is flat at room temperature for several hours. We can use this time to deposit cells and even increase the temperature to 37 degrees Celsius. This gelatin which is here gets dissolved and the bilayer rolls and makes the tube. This approach can be used for encapsulation of cells, like it was shown here. Neural cells were encapsulated in this case. So practically, one can also further extend this approach. One can deposit basically the materials the cells adsorb, and basically these patches can be surrounded by the material which the cells do not adsorb. So practically, we'll be able to selectively deposit cells on these stripes. As a result of shape transformation, we get the tubes where cells, for example, land, and the areas where cells will not be. So practically able to convert this complex two-dimensional cellular pattern in the complex three-dimensional cellular pattern. Third approach consists in the hardening of the, softening of the hard layer. Idea is the following: we again have a polycaprolactone gelatin layer. In this case, polycaprolactone layer is thicker than in previous case, so even the swollen gelatin is not able to deform it. But increase of temperature leads to the softening of polycaprolactone just because it melts. As a result, swollen gelatin is able to deform the soft polycaprolactone, and the bilayer basically rolls and makes a tube. Approach works very nicely. Although we demonstrated this approach on example of polycaprolactone, which has a relatively high melting point, 65 degrees Celsius, this approach can easily transfer to the other polymers which have lower melting points, like for example polycaprolactone polyurethanes, which have melting points around 30 degrees Celsius. The fourth approach is a use of a shape memory polymer. So practically, first fabricate object with certain kind of permanent shape like this, then basically bring to the temporary shape, flat one, and then again stimulate the shape transformation of a temporary object and the permanent one by applying, for example, the temperature. It was demonstrated on the example of the formation of such kind of T-junctions, which are very important elements of the vascular network. So idea here is the following. We fabricate these two elements. This is their permanent shape. Then bring them in the temporary flat shape, like what was shown here, and deposit on the top of each other. Then we apply the stimulus. One of these objects start to fold first, and the second one start to fold later. Why we actuate in different time? Because these two pieces contained a certain amount of photosensitive particles, and basically this object contained more of them, and this object contained less of them. So in this particular case, we're able to somehow, we would say, coordinate the folding two objects in time to allow for fabrication of very complex three-dimensional objects which cannot be otherwise fabricated using a single object. What could be the application of this 4D bifurcation approach? One of them is, for example, fabrication of vascular elements. In this particular case, as I already showed you in one of my previous slides, we were able to fabricate a tubular structure with a diameter ranging from 10 micrometers, which corresponds to the smallest capillaries, to the diameter approximately 200 to 300 micrometers, which is the diameter of the blood vessels, which are most difficult to fabricate. Another possible application of this four-dimensional approach is illustrated here. In this particular case, we encapsulated cardiomyocytes inside the tube. The balls of the tube are shown by the yellow dashed line. What you can see here, the cardiomyocytes are able to beat inside this tube, so means they are not only alive but also keep their natural function. And so practically it was, one can say, nearly the piece of the piece of the cardiac microtissue. Now we try to improve this approach. It's known what orientation of the cells is very important for the proper function of any kind of muscle tissues, cardiac tissue and skeletal muscle tissue. So we fabricated a structure with aligned fibers, so the cells can align along the fibers. The fibers can be fabricated using electrospinning or other approaches, like for example melt electrowriting. As a result, we get the tube where the cells align them along these fibers, And what you can see here, for example, if you carefully open this tube and apply electrical stimulation, you can see contraction of the muscle cells. So practically it means we obtained the scroll, which is formed by the layer of the polymer and the layer of the layer of the skeletal muscle cells, and the skeletal muscle cells formed a continuous structure, and it was not only alive but also able to keep its natural biological function. Another possible application of the 4D biofabrication approach is regeneration of neurons. It is illustrated here. Imagine you have two ends of a broken neuron. You wrap them by the shape-changing layer. So practically this shape-changing layer simply protects two ends of a broken neuron. So that nothing comes in between, but nothing else basically hinders they grow in the direction of each other, and this grow in the direction of each other must be provided by these fibers which form this bilayer. So practically the cells try to align them along these fibers, and these fibers must cause the basically growing of the cells, broken ends towards each other. Another possible application of 4D biofabrication approach consists in the assembling of multiple tubes, which can be either filled cells or can be without cells. Such kind of a structure, as illustrated here and looks like this one, mimics the structure of a cortical bone, which is also formed by the assembled tubular structure. So potentially, one can use for the 4D biofabrication approach for fabrication of the also cortical bone. It was a short overview about our activities in 4D biofabrication approach. Although we are still in the very beginning, we were able to show like suitability and of the 4D biofabrication approach for the fabrication of muscle tissues. It could be skeletal muscle tissue, it could be cardiac tissue. One can use it for fabrication of vascular structures, assistance with regeneration of neurons, and also potentially one can mimic a structure of the bones. At the end of my talk, I would like to show you simply make some kind of short discussion about where shall we go and what basically shall we do in this field of 4D biofabrication. From my experience, I definitely would like to tell you what we need to have a material with tailored properties. We need to have a possibility to design materials with tailored properties, with targeted properties, and these properties must be predictable. For example, having a huge database of the materials with well-defined properties, well-characterized properties, and analysis of this database using artificial intelligence would definitely help us in the development of the materials with targeted properties. One of the main problems in this field is what the ways how the materials are characterized in the paper makes this prediction using artificial intelligence is very weak. Materials are often not properly characterized, or their characterization is insufficient. So practically we need much more information about the materials than it contains in the papers. And if we talk about fabrication approach, many people like to use 3D bioprinting or 3D printing. I thought it is simply one of the possible methods for fabrication of the structures. Practically, we need to think a bit in a broader way and try to go like it is shown in this video. Which are basically found on YouTube. It is a BMW factory where the cars are produced. So practically, these cars are produced from the parts which are basically produced by different kinds of methods. So practically, in this particular case, a variety of technologies, additive, subtractive, and formative technologies used for fabrication of parts, and afterwards they assemble. So practically, we have to start to move from only 3D printing, 3D bioprinting, to the more complex, like factory-like vision, where different technologies are combined each other, and practically we need to develop or think about the factories for fabrication of the organs and tissues, not only the simple devices which are able to do it. Most probably only for the bioprinting will not be able to do it. We need to combine different materials in one device or in one factory. At this point I would like to finish my presentation and I hope you like it and I'm ready to answer your questions. Thank you very much.